So we've been talking about acceleration, and in class today you got a chance to practice using the big four kinematic equations, right? These big four. Hopefully you're getting more comfortable using those and applying them to different word problems. We're going to talk about a specific constant acceleration problem that you will see time and time again, and that these big four are going to help you solve time and time again. So the concept of free fall or acceleration due to gravity is wicked cool. You can apply this to lots of things in your life, and we're going to see it over and over again in this course. But basically, the idea here is that, right, there's this thing called gravity, right? It acts on things on and around Earth, right? Gravity is a force. We'll talk more about that in our next unit. But the force of gravity results in an acceleration. Okay, so every object that is on or near Earth feels some acceleration due to the force of gravity. This acceleration due to the force of gravity we denote as little g. Okay, there's a big G, but we'll learn about that later. And little g, scientists have figured out, is approximately equal to 9.8 meters per second squared in the negative direction. We generally think of up being towards the sky, right, and down being towards the center of the Earth. Up is positive and down is negative, so we tend to think that the acceleration due to gravity is towards the center of the Earth, so it is negative. So this value g it's an acceleration, right? It's an acceleration that we can apply to any of the big four equations, just as we have for cars or buses, right, or people running. But now we're flipping it, right? When we were talking about cars, right, we were looking at motion in one direction, but it was on, right, sort of a horizontal direction, right? And we denoted one side as negative and the other side as positive. Now we're talking about when we're looking at free fall, right? We're going to be looking at objects moving up and down. And for the most part, up is going to be positive and down is going to be negative, right? We're very rarely going to switch those just because we intuitively think of up as being positive and down being negative. So we're still working in one dimension, right? But we're flipping our number line, right? We're now moving up and down as opposed to side to side. So what does this look like, right? What does incorporating the acceleration due to gravity look like in a word problem? So I have an example here, right? This question gives you very little information. It says a rock is dropped from a height 15 meters above the ground. How long will it take the rock to hit the ground? Okay. There is not a lot of information in here, but there is enough information for you to figure out how long it'll take the rock to hit the ground. So let's see what kind of variables we have here. Well, we're given a height, right? I like to draw a picture here, right? So 15 meters. Here's the ground. And, you know, maybe we've got a guy up here on a cliff and he's dropping a rock, right? So this is 15 meters. Down here is 0 meters, right? So in telling us that it's a height of 15 meters, we've actually, we're given the displacement, right? The initial height is 15 meters, and the final height is 0 meters, right, when it hits the ground. So 0 minus 15 is going to equal negative 15 meters. That's our displacement. So it also tells us that the rock is dropped, right? That means the person is just kind of holding it out to the side, right, initially, and then lets go of it. They don't throw it. So what is the rock's initial velocity if it's dropped? It's 0, right? As the person's holding that rock, the initial velocity is going to be 0 meters per second, right? And then they drop it and it falls. Cool. We are also given, right, a acceleration. Not explicitly, right? But the only thing that's acting on this rock once the person drops it is gravity. So we can assume that the acceleration is going to be negative 9.8 meters per second squared. All right, so let's see if we have, so we're curious, we want to know about delta t, right? We don't really have a delta v possible. We don't know what speed the rock was moving at the bottom here, so we're not going to really want that in our equation. But we want to know delta t. So let's scroll up and look at our big four. Right, so remember we didn't have a velocity final. We did have a velocity initial though, so this equation here, right, where v final is missing might serve us well. It's got all of the variables that we identified, right, and we would be able to solve for our delta time. So let's go ahead and use that one. Copy that down here just for memory's sake. So that's delta x equals our velocity initial, delta t, plus 1/2 acceleration delta t squared. Okay, so now we just gotta you can plug in the numbers or manipulate the equation. I personally like to plug them in and see what pieces of this I might be able to get rid of, what might simplify. Times delta t squared. Okay, so just on an initial look, right, this term here is going to go to 0, right, because it's something multiplied by 0. So I can just kind of get rid of that, right? Then we've got negative 15 meters divided by 1/2 of 9.8. That is 4.9 meters, right? So divided by negative 4.9 meters over seconds squared equals delta t squared, right? So you might need your calculator for this one. 15 divided by 4.9, that's going to be about 3.06 seconds squared, okay? And then we need to take the square root of that. So we need to take the square root of that to get the answer that we're looking for. And get my calculator to work. Let's see, square root of that is about, right, so we squared both sides. Square root of a square root is just the regular term. So now we get delta t equals 1.75 seconds. Cool. So it'll take 1.75 seconds for that ball to fall 15 meters, right? The only thing that we knew was from the question was how high it was dropped from, right? We had the acceleration provided because the only thing acting on it is gravity. All right. So we'll talk more about this number, negative 9.8, in class. It's not always the same. It can change very slightly depending on where you are on Earth, but more on that later. Go ahead. I would definitely copy down this question into your book for your notes. Make sure, again, that you have these 4 equations somewhere in your notes. They are very important. All right.